Welcome to this next video lesson. We're going to be talking about example number 6, which is to change this expression into a circuit. So the first thing that I like to do, because I'm so familiar with like an engineer's notation, is to convert this. So for me, I see this. I see P, and this is the OR gate, so that's going to be a plus symbol. And then with the parens, the not of P is like this. This is AND, so we'll just put a dot over here, the not of Q. So from an engineer's perspective, this is what I see. Well, we really don't need the parentheses, so let me see if I can just select those and select this. That's fine. P, OR, and then collectively, the not of P and the not of Q. So that's an OR gate, a couple of NOT gates, and an AND gate. Well, the first thing that I'll do is to write the inputs, which we have over here are P and Q. And let's take care of this part first, the knotting of these two items. And so I'm going to insert a NOT gate, not only for P, and let me arrange that like that. Actually, let me bring that forward because I'm going to have to split it up. One more. Let's see here. Like that. And then I'm also going to insert an inverter for Q, like this. It looks like both of these are going to be ANDed, the not of P and the not of Q. So I will bring in an AND gate. And let me then connect these two, like that. And like this. Whoops. I need to go a little bit more. And this one went too far. Something like that. So the output over here, since this is going to be P naught, and this is going to be Q naught, and then I'm ANDing P naught and Q naught, so the output over here is P naught, Q naught. Now, that is going to be ORed with P. So what I'll do is extend these a little bit further to the inputs, like that. And I'll bring in an OR gate. And let me raise that up a little bit like this. So one of the inputs into the OR gate is, oh, I didn't quite make it here. Like that. There we go. One of the inputs is P naught and Q naught into an OR gate, and the other input is P. So let's see if I can make this trace from here to here, from here to here, from here to here, and then finally make the connection. So this is P coming through. Now this is the same connection here, so I will make a little dot right here to indicate that this is really soldering this wire that's going from here to here and this wire that's being split. Notice that I don't put a dot here because there really is no connection. I guess I could have drawn it outside if I wanted to do something like that, so I didn't get this cross. But that's how we notate this. If there really is no connection, you just don't put a dot over here. This is a separate wire going into this NOT gate. This is a separate wire going into this OR gate. And now this is going to be P ORed with P naught Q naught. So this is really the same thing as P ORed with, and then over here I have P naught and Q naught. Okay, so that is the circuit representation. And in the previous videos I didn't create the truth table first. Let me do that now. So let's say that I have a little box here, or a chart that I can make to show me the output. And let's see here. So this is going to be one possibility, two possibilities, three possibilities, and then four possibilities. I'll extend this a little bit. And my two inputs are P and Q. And just extend these a little bit. So I have P, I have Q, And then, of course, I have the output. I'll just abbreviate that with out. The possibilities are that both of these are false. P is false, Q is true. P is true, Q is false. And both P and Q are true and true. I'm just simply counting in binary, 0, 1, 2, 3, for the 4 possibilities. All right. Well, what will happen? Well, first of all, anytime that P is true, true or anything is true. So anytime that P is true, the output is going to be true. All right. How about this? Well, anytime that this is true, that is the not of P and the not of Q, if this is true, then the OR gate is going to be true. So how do I get this to be 1? Well, if P were 1, the not of, I'm sorry, if P were 0, 0 inverted is 1. If Q were 0, Q inverted is 1. 1 and 1 is 1. So it looks like when both of these are 0, the output is 1. And so that's what I have over here. Because again, 1 inverted, I'm sorry, 0 inverted is 1. Q inverted is 1. 1 and 1 is 1. And therefore that goes through the OR gate, which 1 or anything is 1. So when both of those are 0, then we have this. Now, this is an interesting case. If Q is 1, then that means that the inversion of that is going to be 0, 0, and anything is 0. So the output over here is 0. P is 0. So that means 0 or 0 is 0. All right. So this is the truth table for this expression or for this circuit. And what I'm going to do now is I'm going to design this circuit in the Logic Lab website, and then we'll test it out. So let me switch over here, and I'll have 2 switches. And it looks like those 2 switches have to go through an inverter. Now, because I'm going to have to split P, I'll use one of these extra items, specifically one of these splitters. So I'll go over here like this, connect these 2, and then I could split the signal of P. Specifically, one of them has to go into an inverter, and the other one will go into an OR gate. So let me go over here back to, let me see, an inverter. So that's going to be not. And we also know that our other signal, right, because we have P going into here, Q going into, actually Q does not, yeah, I'm sorry, yeah, Q does go into a not as well. So P will go into here. Q will go into here. Okay. All right. Now it looks like the not of P and the not of Q go into an AND gate. So I'll just simply bring an AND gate over here and bring both of those inputs into an AND gate. And then eventually that AND gate output goes into an OR gate. So I can just bring this over here. And eventually goes into an OR gate. Okay, what is the other input of the OR gate? It looks like it's the signal P. So I just simply take this, go over here, and the Logic Lab, as you can see, will do this. And for the output, we'll have an LED. Like that. Okay, so according to the truth table, if both of these are off, the output is on, or I could say, you know, false. If both the inputs are false, the output is true. I could say if both of the inputs are 0, 0, the output is 1. I mean, there's all kinds of ways of stating it, right? Let's see, how about this? If P is 0 and Q is 1. If P is 0 and Q is 1, then we should have false or off. Good? How about if P is on and Q is 0? So if P is on and Q is 0 or 1, 0. Then we have a true state. Yep. And if both of the signals are on, or both the switches are on, then the output is on. And sure enough, on, output is on. And that's it. So this is Professor Robert Solis. I hope this video lesson was helpful. Have a good day. See you next time.